Universidad de Montreal. Garry está aquí gracias a que los colegas de Tucumán se organizaron, lo trajeron, aprovecharon algún dinero que viene del gobierno de Canadá y vino a dar algunos cursos a Tucumán. Y nosotros nos aprovechamos de que los aviones paran en Buenos Aires, entonces siempre tenemos la ocasión de tener visitantes de esa manera. Garry hizo su trabajo de doctorado con Jean-Marie Len, quien me imagino que todos conocemos, y así que desde ahí tiene en su trabajo una influencia de la química supramolecular, o por lo menos la visión de ir en esa dirección. Y después hizo una estadía postdoctoral en Italia, en los laboratorios de Vincenzo Balsani y Sebastiano Campagna, así que fue introducido a la mafia del rutenio, así que hay que trabajar con rutenio también, cosa que nosotros aquí conocemos bien. Así que bueno, rutenio, así que estamos hablando de estados excitados y nos excitan los estados excitados, así que vamos, él también está interesado en green chemistry y tratar de aprovechar esa energía para hacer una química interesante, así que lo dejo con él. Gracias, Garry.
Thank you, Luz. So thank you all for coming today. So, yes. Thank you. Okay, so I'll be talking to you about our some of our recent work in the University of Montreal. So I am an inorganic chemist, but a coordination chemist. So we do some limited organic chemistry to make our ligands, which provide a lot of the new properties to our metal complexes. So I'll talk to you about that. So I just want to show you where I am, in Montreal. So that's in the eastern part of Canada. And this is in Quebec, which is a province of about 8 million people, and 7 million are more French speakers and 1 million who speak a variety of different languages. I'm originally from Winnipeg, so right in the middle of the country here. So you're lucky to be close to the water. So it's about 3,000 kilometers to the Pacific Ocean, 3,000 kilometers to the Atlantic Ocean, but only about 1,000 to the Arctic Ocean. So it's very a landlocked kind of place. So this is the University of Montreal, the main campus. And in the back you can see Mount Royal Park, and that was designed by the same architect who did Central Park in New York City. And here you see the downtown and the St. Lawrence Seaway. So it is one of the bigger universities in Canada, 50,000 students, which I understand is a very small university for Argentina, because Tucumán is about 80,000, more than 250,000 here. So I'm from a small university in Canada. And this is a new building which was finished in 2020. So this is for the sciences, chemistry, biology, physics, and geography. So this is the research wing. And then there's another building about the same size, which is just for the teaching on the other side. So this is the outline of my talk. For the introduction, I'll go over why we need carbonless energy sources. You're all familiar with CO2 and global warming. But we'll try and find some answers, and it's nice to take some inspiration from nature for this, and how we can develop an artificial system to create chemical energy from sunlight. And then I'll talk more specifically about some of the work in our lab, photosensitizer and redox catalyst diodes. So this is a way of combining a photoactive component with a catalytic component. In our case, is to produce hydrogen from water. And I'll show you some recent results with a collaborator from Barcelona, Xavier Sala. So it's more directly from his work. So we provided some of the compounds. So I'm not I don't do a lot of materials chemistry. So I do collaborate for that part of the research. But I thought you might be interested. And then we'll look at the self-assembly of photoactive supramolecular systems. And then after I've shown you all this beautiful ruthenium chemistry, I'll say why ruthenium chemistry is terrible. And then why we should be looking at first-row transition metal complexes as photosensitizers, and how that's very challenging because they're so labile, the complexes. So how do you get these stable complexes with these first row. Don't worry, Lewis, I still love repeating form. And then we'll have a summary and conclusion. And if there's time for the students, and maybe some of the professors are interested, I'll present two programs from Canada. ITAX, that's just the funding agency. So it provides funding for Canadian students and postdocs to come to Argentina if you have a collaboration with the lab. It also funds Argentinian students and postdocs to go to Canada. And then there's another program called the Emerging Leaders in the Americas, and that's more specifically for Argentinian students to go to Canada. So I'll talk a little bit about that if there's time at the end. So one of the reasons why we need to find new sources of energy is because of the world population increase. This is from 2018, and you see that India and China all have over 1 billion people. And if you want to raise people out of poverty, one of the best ways is to provide, obviously, jobs, but this requires energy. They're going to want to buy cars, and they should have every right to buy a car. Hopefully we go to electric sooner, but anyway, it takes a lot of energy to get people out of poverty, and as we have an increasing population, more energy is going to be required, and hopefully this does not lead to more production of CO2. I just found this very interesting. This is from 2024. So Argentina, 47 million, Canada, 41 million. So the size of, well, population size, not size of the country, but population size is roughly the same. So this is the main problem, this idea of global warming. This is from NASA in 2015. And the deep red is a 2 degrees centigrade rise in temperature compared to data from 30 years before. And deep blue is a 2 degrees lowerings. But you can see in 2015, overall, the planet was getting warmer. There are two exceptions. Here's Quebec. So in the north, there's some blue. And the other one, Argentina. So we got a little bit cooler in our northern parts and our southern parts. But you can see the overall trend is this rise in temperature. So what this produces, especially for country, the southern Argentina and northern Canada, is what a melting sea ice heat spiral. So the global temperature rises, this rising temperature melts the sea ice, which is used to reflect sunlight, well, not used, but it does reflect sunlight back into outer space. And if that's not there, there's more ocean exposed, which heats, and which leads to global increase in temperature. So you get this heat spiral increase in temperatures. This is the CO2 concentration. I'm sure you've all seen this kind of graph. So from 1960 to 2021, and you see this steady rise from about 315 ppm to about 418. And the latest result that I saw from this website was 430 ppm from this year. Again, this idea of thinning of ice, a loss of 413 gigatons of ice per year, and 12.8% per decade loss in Arctic sea ice. And just to give you some more recent data, this is from the Copernicus European Union satellite for January 2025. And same idea, red is an increase in temperature compared to 30 years before, blue is a decrease. And you can really see the problem is the Arctic is warming and the Antarctic is warming. So this is really a global challenge to get away from this, the use of CO2. So, where can we take inspiration? So natural photosynthesis is a very good place to start. So green plants and algae have these chloroplasts, and in the thylakoid membrane you can find different photosystems. So photosystem 2, photosystem 1. So very elaborate structures. Of course, they capture the light energy through chlorophylls and carotenoids. I'll show you that in a second. But essentially, you excite this P680, which is two porphyrin-like molecules, and then you have a series of electron transfers to quinone B, which is reduced twice and then protonated. And on the other side, through a tyrosine, you have a manganese cluster that is oxidized, and then you oxidize water. But what is very interesting in this process, of course, is this quinone B. If I just show the basic structure, you can see it, of quinone. So essentially, it's reduced to a hydroquinone. So that's the process that happens in the cell and just outside the cell. But this, of course, is plus 2H plus 2 electrons. This is minus 2H plus. minus 2 electrons. So essentially we have everything for hydrogen gas right here. 2 electrons, 2 protons. So what we want to do in a way is short circuit what goes on in a natural system and be able to use this chemical energy for production of hydrogen or other value-added products. You could think of reducing CO2 to formic acid, a very small process, or multi-electronic processes reducing CO2 to methanol. Now, if you burn the methanol, of course, you produce CO2, but at least it's carbon neutral. If you can capture the CO2 and convert it to methanol, and then you release CO2, but you capture it again, then there's at least a carbon neutral way of using carbon-based products. So essentially what we want to do is take the special pair, and instead of having photosystem 1, we'd have some way of producing hydrogen gas and oxidizing water to form O2. So the challenge here is not to duplicate the structure, obviously. So my estimate is 1 million postdocs, it takes them 1 million years to reproduce this structurally. But we want to reproduce the function of these photosystems and try and have a much simpler system to do it. So just to take you on the side, so I'll talk about this hydrogen production in the first part, then I'll talk about assembling light harvesting complexes. So this is purple bacteria. So these light harvesting complexes surround the reaction center. And so you can see a picture of them here. So there's 16 subunits in light harvesting complex 1, 8 in this one. And so this is using self-assembly. So weak forces, hydrogen bonding, pi stacking, van der Waals forces, electrostatic interactions between amino acids. And what you see if we close in on B850 is these 8 subunits coming together, but there's no covalent link between them. This is really just through electrostatic and all these supramolecular non-covalent forces that bring them together. These are the alpha helices, so these are full of side chains of amino acids that can interact with each other. And then you see the pi stacking here between, so in one subunit there's 2 B850s plus a B800 and another carotenoid, but you can see how they can pi stack along one another. And this is vital for energy transfer because once you excite one of them, the excited state, the exciton, just travels around until it ends up in the reaction center. So that's critical of the component. And what I like about this, if you zoom in on the, these are just models, these aren't from crystal structures, just so I'm clear. This interaction between a histidine, which is an imidazole side chain, and you see metal ligand bonding. So you do see some coordination chemistry, even in this natural system, and some more hydrogen bonding. So the idea is, can we use self-assembly to bring together a larger structure, but also that it is still photoactive? So that would be the idea behind this. So can we use self-assembly to do these light harvesting complexes? So you want high energy absorption, so I indicated with blue, and then low energy absorption, so with red, so that you have vectorial energy transfer to a primary photosensitizer, just like P680. And then you'd have some electron transfer to an acceptor, which becomes A-, and then the donor donates an electron to P+ to regenerate the photosensitizer. So you have D+ and A-. So the key here is you don't want charge recombination. That kills everything. It just goes back to the ground state. So you need to transfer this electron to a catalyst, and this is what we do, this hydrogen production. And on the other side, you oxidize water oxidation catalysts. So these are the two other aspects of this work. So let me show you now some of what we've done in this photosensitizer redox catalyst dyads. Before I'll just show you the classic ruthenium trisbipyridine. Here's the classic review. I think it's all close to 10,000 citations, I think, or something. It's something crazy anyway. It's a very high number of citations. So you see the reason why it's used so much is that you can see a nice absorption in the visible. So of course the ozone blocks the UV absorption of the bipyridines. So it's an epsilon value of 15,000. Very nice reversible electrochemistry. You can imagine you're exciting the molecule, you're transferring this electron away. This has to be reversible. If this decomposes once it's oxidized, then it's no good. You're just consuming all of your photosensitizer. So reversibility is important. And then you have this long excited state lifetime. So the essential key of the lowest energy transition is this metal to ligand charge transfer. And this EG star is very much higher in energy. So there's a strong interaction with the BIPs with the ruthenium. And the HOMO is now ruthenium-based and the LUMO is ligand-based. So you see the key number here is 850 nanosecond lifetime at room temperature. But let's just rearrange those ligands just a little bit and make it terpyridine. So what you'd see, there's still 6 pyridines attached. So it should be the same, but no, it's 0.25 nanoseconds. So a massive loss in excited state lifetime. And the main reason is this EG star comes lower in energy. Why? Because now these nitrogens, you can see the angle here, 156 degrees, don't interact strongly with the DZ square orbitals, so this is much less high in energy. So at room temperature, you have an MLCT, but it can populate this antibonding orbital. You get vibrations, stretching, and deactivation of the excited state. So that's why it's so low in energy. So I'll show you now how we get around this problem. How can we increase this energy, excited state lifetime, to be able to do chemical reactions. So this is a wonderful review by Tony Jobet from in Catalonia, where he showed in this review that you excite this photosensitizer, you transfer it to a catalyst, and then you can reduce protons to hydrogen or CO2 to different formic acid or methanol or other things. And then on the other side, you give the electron to the photosensitizer. So what we're going to use for our research is cobalt oximes, or cobalt. I always want to say cobalt oximes, but cobalt seems, there's no T. Here's an example of these photosensitizers, so rhenium, iridium, platinum, and you can see modest production of hydrogen using these systems. So these are using second and third row transition metal ions. So one question is, can we get away from these? And then here's an example that I'm going to use as our model, is this original work over 40 years ago. Jean-Marie Laine produced this system, having a turnover number of 16, and Fontecave then showed that if you attach it directly, then you get a much better turnover number. This is modest, but he did show in later papers that you get a much higher increase in the production of hydrogen. Because now remember, this is a biomolecular reaction. You have an excited state, and then in the time that you have an excited state, this catalyst has to diffuse close to your compound to get an electron transfer. So what you do is you excite this. When it's in one molecule, you excite it, and the electrons are transferred to cobalt, and the cobalt produces the hydrogen. So these are the systems that we developed. So this tris pyridyl terpyridine, and if you do what we're about to show you, if you do it just on terpyridine, the hydrogen is absolutely zero, any kind of light. The excited state isn't long enough. So what we hoped is with this sort of planarity, or close to planarity, it's not exactly planar, but this delocalization on the pyridine will lower the pi star, so farther away from those antibonding orbitals, and we'll get some increase in the excited state lifetime, long enough to transfer electrons to the cobalt. So this is the synthesis. This is the painful part I'm not an organic chemist. So 35% yield, but you can do this by radical coupling and then do purification by column chromatography. The rest is very straightforward. This is a one-plot Kronka type synthesis, 42%, and then you can make this in high yield. And you notice microwave 240, you'd say that's quite extreme, why are you doing that? But you've got to remember that this ruthenium can also bind to these pyridines, so you could get oligomers and polymers. The only thing that's stable at 240 is the chelate with 3 nitrogens attached. So none of the monodentate ligands attached, so you get a very high yield of 91%. So this is the electrochemistry, is, as you would expect, very similar to bis terpyridine or ruthenium, tris bipyridine or bis terpyridine. I'll just show you the photophysics. So the emission energy, or the absorption and emission energy, are at longer wavelengths. So lower in energy, as you would imagine, because we're lowering the pi star level, so our MLCT energy is lower. And you see here an increase in the excited state lifetime and the quantum yield. So this is actually compared to bis terpyridine. So the excited state lifetime goes up 20 times. So this is long enough to do what we need to do with 5 nanoseconds. But what I was really wasn't expecting is the 600-fold increase in the quantum yield. So 0.6% isn't very much, but ruthenium tris by purity's gain is only 9.5. So we're getting onto the ballpark ruthenium tris by purity. So this is the system we're going to use, our photosensitizer, with those pyridines hanging off the end. It forms a bridge to the catalyst, which this is quite a classic catalyst. We didn't invent this. As I said, this came from Jean-Marie Len's work and others. This cobalt DMG compound. And we use triethanolamine as a sacrificial electron donor. And we have a little bit of acid there. For now, we're working in DMF because we wanted to parallel what Jean-Marie Len did. But of course, the target would be to work in water, so use a more ecologically viable solvent. So this is the key. I showed you ruthenium tris by purity and told you how fantastic it is, but this is to show you how terrible it is. Because it works fantastic, so in blue is the turnover frequency to the left, in millimoles hydrogen per mole of photosensitizer per minute, and on the right is the turnover number, and you can see within 20 hours or 10 hours, there's almost no activity. 20 hours virtually gone, 40, there's absolutely no more activity. And you can't have a functional device on the roof of your building if every 40 hours you have to go change your device. So this is, even though it's bidentate ligands, it's still not photostable at 445 nanometers. We use LEDs for this. And the GC, we're using the headspace GC for sampling, so to get the precise amount. So we're sampling every 2 minutes, so we get a lot of data for these. So you can see, so that really decays completely. Now, our complex is not as good, right? The quantum yield is lower, the excited state lifetime is lower. Again, this is in the presence, obviously, of the cobalt catalyst. And you can see how the decay is much slower. So a slower loss of activity. The turnover number is still going up, but after 168 hours, we decided to end the experiment. It's long enough. Eventually it would get up. It would if we continue to get to the same value as ruthenium tris by purity. Now, if we go to green light, the ruthenium on the right is the ruthenium tris by purity. It still functions. It's still producing hydrogen now up to 60 hours, so it's not as unstable. And ours does produce hydrogen. The decay of the stability is not as rapid. I forgot to mention, though, even in this experiment and the others, if you add more ruthenium tris by purity, bang, the hydrogen shoots up again. So it really is the ruthenium. It's not the cobalt that's decaying. It's the ruthenium tris by purity under constant irradiation that decays. And this is the really nice result. So at this red light, 630, I didn't make the point, but the absorption of this, our compound, tails into the red, and it still absorbs at 630 nanometers. So at this wavelength, no terpyridine complex functions. The ruthenium tris by purity does not work, it doesn't absorb. But our system does absorb, and you can see, although it's very slow, the turnover frequency and the turnover number are maintained after 210 hours. So with red light, there's no decay. Now the quantum yield is shockingly low. It's quantum yield that we calculated is 0.02%. And I asked my postdoc, are you sure? I mean, don't you mean 2%? You made a mistake? He said, no, I checked it 10 times. But if you can, right now we're using LEDs, but if you can use it from sunlight, you don't really care if the quantum yield is 0.02% if it doesn't decay. So that's really the key. If you can use sunlight, it's a much better. So here, just to say, I'm not. This is the main work of Xavier Sella. I have his permission. I even have his slides. So I'm just going to show you a little bit about these compounds and how you can make them even better if you use nanoparticles or make some sort of heterogeneous system. So his way of doing this is using a Clark electrode. So he's looking at the same reaction, and his ruthenium nanoparticles are the ones that are going to be doing the catalysis to form the hydrogen, and he's going to use ruthenium compounds to do it. So this is just something from the literature where they tried ruthenium tris by pyridine and this organic dye with a different kind of ruthenium nanoparticle. So this is ruthenium 0 on the core and ruthenium oxide on the outside. And what they showed was it doesn't produce at all, but if you use a redox mediator, methylbiologen, you can get electron transfer from the ruthenium to the methylbiologen and then to the nanoparticle of ruthenium, and then produce some hydrogen, but very, very modest. So what Xavier showed, so this really doesn't work, this direct electron transfer doesn't work, but he showed with the help of Mirko Natali at the University of Ferrara, is that if you put them both on a, you put phosphates or phosphorus oxides off the back of the VIPI, it grafts onto titanium dioxide, and you get electron transfer into the conduction band of titanium dioxide, and then directly to the ruthenium nanoparticle. And there you can produce hydrogen. So you need this, it's still a mediator, but it's the conduction band of titanium dioxide. So this gave Xavier the idea to look into ways of grafting molecules to the surface of the species, and can we get hydrogen production without a mediator. And in 2017, we published this paper and had a communication before about these kinds of compounds, which these quaternipyridines, excellent properties. The quantum yield is almost double. The lifetime is also almost double. The steady-state lifetime. So he contacted us in 2019. We sent him 100 milligrams of the compound, and then COVID hit. As you know, everything went to hell then. And so I forgot about it. And then just last year, he contacted me and said, "Oh, you remember you sent me those compounds?" I'm like, "Actually, I don't." So he sent me the email that we were corresponding. Oh, okay, but I don't remember many things pre-COVID, so that was a long time ago. So we collaborated, and now these are some of the results that he has. So we've recently submitted this paper. So this is for those who are interested. This is how they make it. So it's cyclooctatriene and cyclooctadiene ruthenium compound, and then using hydrogen in the presence of our dye ruthenium compound, you get this ruthenium nanoparticle with these bound by these pyridines. And then their technique, which made it very useful, was they open it to air over 28 days, a slow amount of air, and then you form this cover of ruthenium oxide, and then you still have the ruthenium 0 and maybe some ruthenium 2 in the center. So these are the size of the nanoparticles using 0.1 equivalents of this, 0.2, 0.3, 0.4, so roughly all the same size of the nanoparticles. He also showed by elemental analysis of the content of the nitrogen and ICP for the content of the ruthenium, that as you use more, you do this reaction with more equivalents of this dye, the photosensitizer increases and the total ruthenium goes down. Now, of course, these were washed profusely with solvents to make sure, until there's no color in the solvents, that there's no extraneous ruthenium complex. This is some other work, so some TEM, and showing on the surface you could also see this ruthenium oxide and also see ruthenium itself. So you could see this ruthenium oxide outside, and at some points there were exposed ruthenium 0 on the surface. You don't see it well here. Oh, you can see it. And there were some points, even he said it takes a bit of imagination. There were some points that you could say that perhaps are the ruthenium core on the surface, but even he said that's a little much. Some other experiments we did, or he did. So you can see here, this is the core complex. This is so the nitrogen 1s using XPS, and you can see here these are coordinated nitrogens, and this is the uncoordinated. I apologize, it's hard to see just where my pointer is, and that's 2 compared to 6. And then here you can see that this value is much lower, and that's presumably due to the fact that 1 or 2 of the nitrogens is coordinated. So there's very little free nitrogen once it's bound to this nanoparticle. And this is the hydrogen production results. So with 4 equivalents with 1 equivalent and 2 equivalents, there's very little hydrogen produced. But when you have 3.3 equivalents and 0.4 equivalents of the ruthenium, then you start getting production of hydrogen after an induction time. And how he explained, and this is just to show that before irradiation, there's a lot of ruthenium 4, this is again XPS, and then some ruthenium 2 in the core, but after irradiation there's a noticeable shift towards ruthenium 2 and ruthenium 0, so that you have the oxidized outside, but once you transfer electrons from the ruthenium into the core, you're starting to get more towards ruthenium 2 and ruthenium 0 because of this reduction by the photosensitizer. So before, this is the size of the particles before irradiation and after. So the particles aren't really affected, the same size. But really what you can see is more and more of the ruthenium is leaching off the surface. So before the experiment, remember, they really washed it many times, and there was no leaching. After the photochemical reaction, so we're losing some of the photosensitizer. And what turns out, this is related to the induction time, you get a huge loss of the photosensitizer. This is 0.3 equivalents. And then the hydrogen commences. So remember, there's no cobalt in this. It's just the photosensitizer. So what they believe is that there's this second coordination sphere of photosensitizer. It is not able to produce hydrogen, but it will, over radiation, leach away. And then the primary core bound to the surface, that's this blue one, that's when the hydrogen produces. And that's the one that's producing the hydrogen in this by electron transfer, reduction of ruthenium, and binding with hydrogen to the core. Okay, so now we'll get to, so that was the hydrogen production part. How can we assemble these light harvesting complexes? I don't know if any of you are familiar with the work of Makoto Fujita, but in 1990 he showed something that I thought there's no way this will work. So he showed that if you mix 4 equivalents of this, the S here is a solvent, not sulfur. So it's cis protected, so this is a 90-degree angle with 180 degrees in the ligand, you can get this molecular square. So the reasons behind this, you would imagine, why doesn't it just form a polymer, or why don't you have a ligand? The yield is exceptionally high. And so what you have is a maximum occupation of coordination sites. So if you have this, you can imagine this site is infilled, so enthalpically that's not so good. There's only a salt material, and enthalpically that's not so good. So if you form the square, then enthalpically it's better. And then you might say, well, what about if you spin this 180 degrees and you start forming this? You start forming a polymer. So enthalpically that may be favored because of all the coordination, but you're forming one polymer. So entropically it's not favored because you don't have many, many, many of these smaller subunits. So entropically it becomes disfavored. And the key to all of this is reversibility. So if you start forming this polymer, of course there's bond forming and breaking. Palladium-nitrogen bond isn't so strong. But if this breaks in the polymer, it becomes intermolecular for this to return. It diffuses back. And what I like to call, if you have this, the square, it's an intramolecular return. So I like to call this the supramolecular chelate effect. It's a supramolecular assembly. If one bond breaks, it's right there ready to come back and form a bond again. So reversibility is the key. So this is 99% of the research, they use heat as reversibility. So this works at room temperature, but if you use platinum, you have to heat it to 100 degrees. And I'll show you what we try to do and show that as long as it's reversible, so why not use light? This is the formation of the square. Makoto and then Peter Stang did a lot of research, and this review showed you can get all different kinds of forms depending on the metal and the ligand, 3-dimensional. But of course, this was around the time that MOS became really big. So if you go into 3 metal organic frameworks, you get the full thing. So this is Fujita's work, 180 degrees for the ligand. With the arrow, that's the nitrogen lone pair, and 90 degrees on the metal. So this is a 4+4 approach, or you can reverse them and still get a square. So our approach was this. It's what we call a directed approach, where you have a site on the metal complex that can accept the lone pair, but also an extra lone pair on the complex which can go into the site. Of course, it can't go into one, so what you might get here with heat is this molecular 4 times 1 assembly. But what we really were interested in is using light. Because if you remember, I showed you that graph with that MLCT, or the pi star, and you can say if you use a Jablonski diagram, that the MLCT is very close in energy to the metal centered orbitals, these EG star. So at room temperature, you can populate them. But if you can excite, if it's close enough in energy, at room temperature, you can populate the EG star. It's the EG star that's breaking the bonds and giving you the reversibility. So can light induce sufficient reversible binding and formation of molecular square? So we were inspired, this is Dave McMillan from many years ago, and more recently Claudia Turow, showed in different, this is also used for in bio applications, photoejection of molecules for bio applications. So this is just a terpyridine with a pyridine, and this is a bipyridine, either sterically hindered or not. And she showed with light you could photoeject the pyridine. So this is well known, photoejection of ligands with light. So what we were interested with this ligand. So now you see the acetylnitrile and this lone pair here. So this is the metal site, a 90-degree angle to this nitrogen. We added the terpbutyls just to keep it organic solvent, soluble, so we added terpbutyl groups. So we're using light at 452 nanometers, we could assemble this molecular square. Now if you try and do this reaction at reflux and acetone, it's not very hot, it's only 60 degrees, but there is no formation of a molecular square. You barely get any reactivity at all. Acetylnitrile is too strongly bound. But what we're doing is, with the light, you can photoeject acetylnitrile, which is important. But more critical is you can photoeject the pyridine, because if you start forming the polymer, of course, it's a pyridine that's bound. That's the one you have to break. So it's not perfect. So this proton here is telltale. This is the proton right here, close to the triple bond of the cyano. So as soon as you start irradiating, it disappears. There's other oligomers, of course. And then after 24 hours, you can still see a little bit of evolution. So the yield is only 80%, so we have to use size exclusion chromatography, so our species goes through first. But we have other evidence that there's dimers and trimers and things. And this is another, so it has high-res mass spec and elemental analysis. But this is DOSY NMR, so it's a diffusion NMR. And you can see blue, green, and pink in here. These are all mononuclear ruthenium compounds. They all diffuse about the same, but our assembly diffuses differently. And by calculations, you can show it's about 3.8 times bigger than these species here. And then we were fortunate enough to get an X-ray crystal structure. The terpbutyls have been removed, so it's a PF6 for clarity. The R value is not so great, it's about 14%, but at least it shows it's a square, it's not a triangle or a pentagon or something else. And the angles are close to 90 degrees in the corners. If you look at the electrochemistry, I won't go into detail, but it reduces on the two ligands here, the two ligands here, and then the two BIPs and the other two BIPs. So you get four two electron, they're not two electron processes, the electrochemists will be upset with me. They're two simultaneous one electron processes. So you get 8 electrons into the system with reduction chemistry. The interesting part comes from the photophysics. So this is 9, compound 9. You can see 9, 8, and 9. So absorption is much stronger, obviously, because it's 4 times each subunit. But if we compare some of the properties, so it's the lowest wavelength. When you add the other metals, the ligand, it lowers the pi star even more. So it's quite a low energy, long wavelength, low energy emission at 415 nanometers. This reference compound emits at 715 nanometers, and the lifetime is only 1 nanosecond. Here we have 130 nanoseconds. So this is 130 nanosecond excited state lifetime. So much more than the other one I showed you was only 5 nanoseconds. So here we're up to 130 nanoseconds. And what I found surprising is almost 1,000 times greater quantum yield. So you're up to 1%, which is not bad for ruthenium terpyridine compounds. So we still have to use this compound for hydrogen production, etc. But we sort of showed that you can use light for reversibility instead of just heat. So after all that ruthenium, why is ruthenium bad? So it's not bad, but there's been more and more research. Oliver Wenger, Katja Heinz, Kenneth Valnok in Europe especially, they've been working on these first row transition metals, getting away from second and third row transition metals because they're toxic, more scarce, and cost much more. So this is a logarithmic scale. For example, if you compare the iridium in the crust compared to iron, of course there's lots of iron, so that's a big target for photochemical activity. So you can have a kind of sustainable photochemistry for these kinds of devices that I'm talking about. So this is our ligand design, so it's not the polypyridine, there's still nitrogen, but these are called amidines, so NCN bond, and this is a reaction with a phosphorus silicon polymer that is very easy to make, and it's very good at dehydrating. Silicon likes oxygen, so does phosphorus, so you can really use a double dehydration to get this amidine, and then using metachloroperoxybenzoic acid, it's just you can add the oxygen to this group. So this is we call amidine N-oxide or AMOX, and you can make a wide variety of these with different R groups. I'm just talking about the R here in the middle as being methyl or triphenyl. They're very similar. So this forms, you can do a reaction with cobalt-2, and it deprotonates this, the acetate deprotonates this, and it oxidizes in open to air, and you get this cobalt-3 compound at relatively good yield. Very stable, you can run them on a silica column, they come down nicely, and it's quite nice. So the very interesting electrochemistries, very reversible oxidations, plus 0.59 volts for both of them, plus a second oxidation of plus 1.25, and an irreversible reduction. Now you remember with ruthenium, there's a metal-based oxidation and a ligand-based reduction. This is exactly the opposite. This is very electron-rich, this NCNO, it's an anionic ligand. So the pi level is very high in energy, so you're oxidizing the ligand. So this is two reversible one electron oxidations. The reduction, we believe, is irreversible because once you get to cobalt-2, it kicks out a ligand. It only wants two anionic ligands. So as long as you're doing oxidative chemistry with this, it should be good. So if you're transferring an electron to something, it'll be stable. It won't want to accept electrons. So it's not as versatile as ruthenium because ruthenium can do both. But if you're giving electrons away, it's quite stable. This is the DFT, so this kind of confirms what I just said. The HOMO is really 94% ligand-based. Mostly this NCNO, this rich part. And the LUMO is 50-50 cobalt and ligand. So it really confirms that the HOMO is really ligand-based here. And the majority of the character is, well, roughly 50-50. Same for LUMO plus 1 and HOMO minus 1. Now this is where the chemistry is very interesting because it displays anti-Kasha emission. So Kasha's rule states that you should emit from the lowest energy excited state. So this, as you can see, these are the LMCTs. We don't believe they're metal-centered because if you look at it, the epsilon is 500, and that's much too high for metal-centered spin disallowed and symmetry disallowed absorption. So the LMCT is allowed. It's not very high, but it's still 500. And this is another LMCT, and this is well over 1,000. So even though we have these lower energy excited states, it's still, the irradiation is at 280 nanometers, and the emission is at 360, a lifetime of 1.5 nanoseconds, and the quantum yield is about 1%. So we did do some tests, because when we first submitted the paper, of course, they said, how do you know it's not free ligand? And so the wavelengths of absorption and emission are quite different. The quantum yield of the ligand is 10 times lower. It's 0.1%. This is 1%. The lifetime of the ligand is lower as well. Plus, if we do constant irradiation, the ligand is dead in 60 minutes. You can see the absorption just goes away with constant white light irradiation. After 60 hours, the complex barely has changed. So the ligand is only stable on the complex. So it really is much more stable, and you can really think about it. N-oxides aren't particularly stable compounds. So really in the complex, the 3+ stabilizes the anionic character of the ligand. And this is some, just to relate, if you look at molecular orbitals, this is a fantastic paper by Jim McCusker. He really threw BIPI chemistry on its head with this paper, and they even had a science paper after using these compounds for this cobalt-tris-BIPI for photoredox chemistry. Because what he said is, as you can imagine, cobalt-3 is plus, these T2Gs are very low, much lower than ruthenium. Ruthenium would be up here, and you remember from undergrad, ruthenium interacts with the pi star. But now cobalt is so low, it interacts with the pi electrons of BIPI, which is unusual because BIPI is not so easy to oxidize. So it interacts here, so you form a T2G star, but this has much more metal character, because it's closer to the energy of this one. This has ligand character. So the lowest energy transition is DD, and then he went on to use this DD state for electron transfer and hydrogen production. In our case, I showed you, they're super easy to oxidize. So now our pi level is much, much higher. So it's our pi level that's interacting with the T2G with these AMOX ligands, but it's much higher in energy than the cobalt. So now this T2G star is ligand in character, and the T2G is more metal in character. So here that sort of justifies our LMCT. So if we look at the overall landscape, we have some, with our collaborator Sebastiano Campagna, my student Berinda Sa went and showed that this is the excited state that emits. So at roughly 300 or 280 nanometers, you can excite to this singlet ILCT. So that NCNO, very rich in electrons, goes to the pi star of the phenyl and the nitrogen. So that's one of the ILCTs. That one emits. The other ILCT in the center, so NCNO to the center pi star, that does not emit. It decays to the LMCT and then non-radiatively decays to the Rhinestock very quickly, 20 picoseconds. So this, we get the lifetime of 1.8 nanoseconds and the quantum yield of 1%. And you can say, well, why is it disconnected? Why does one mix and one doesn't? If you remember from the LUMO was 50-50 ligand and metal, but the LUMO was principally the pi star of the central ligand. So the metal and the center of the ligand, the central pi star of the ligand, are mixing in that LUMO, and that's why the deactivation and energy transfer from the central phenyl, and the ILCT on the outside, the phenyl and the nitrogens, is disconnected. And you can see from this crystal structure, you imagine you have 9 phenols around this cobalt. They're all going to be roughly perpendicular. I drew them flat, but really, if you think about it, they're mostly perpendicular, so they're just not interacting through the NCNO core. They're disconnected completely. And then to show an application, we haven't looked for hydrogen production with them. We made this one with the pyridine. Our goal was to put them on, to make hydrogen, as I showed you before. But we collaborated with Marek Majewski at Concordia, and he made some zinc oxide nanorods and showed that when there's no illumination, there's no current, but at least on the surface you get the production of current. Without light, there's no current. With light, there's current. So he showed that these can be used for photovoltaics. He was using, I think he was just using white light, so of course he hit our MLCT, our ILCT, that's 1 nanosecond. But sometimes for these compounds, especially titanium dioxide, photoinjection in the conduction band can be very quick. So maybe our 20 picoseconds is long, but maybe not. But there may be applications even for the LMCT. So I hope that I showed you that this tris-pyridyl terpyridine ligand can really be, it's a rather, it's 2 steps, but it's straightforward. Forms these luminescent ruthenium-2 complexes, and these complexes with cobalt DMG produces with red light irradiation for 10 days with no sign of decay. So we're hoping that we can go even further and longer and just get a system where we can set it up and hopefully use sunlight for this process. And this is, again, Xavier Sala's work. This ruthenium nanoparticles based on his original system is based on this phenylpyridine. That's what the PP is, phenylpyridine. So that can be modified with the quarter-pyridine compounds, and then you still get hydrogen production over long periods of time. I didn't make the point then, but it was over, I think he did it for 100 hours. In our paper, when we did hydrogen production just in solution, they were dead after 20. So even that quarter-pyridine compound has the problem that it decays. On the ruthenium nanoparticles, it was over 100 hours he stopped the experiment. So they were still producing hydrogen. So there's something about this heterogeneous. So the homogeneous, I think, is not as good, even though these are bipyridines. There still is photo decomposition. On the core, it was still okay. Perhaps photoinjection was rapid enough to not give it unstable ruthenium compound. And these head-to-tail assemblies of the metallosquares are very efficient using photochemistry. So this shows that you can use light for self-assembly. Oh, sorry. And finally, this cobalt amidine N oxide showed this anti-Cash emission from a high-energy ILCT state into a ligand charge transfer state, as opposed to this low-energy LMCT state, and they display photocurrent grafted to zinc. So I have to thank my students. So the ruthenium self-assembly was Baptiste, the terpyridine hydrogen production, Elodie, Gabrielle, and Olivier, and Arindan and George did the cobalt AMOX work. And Xavier Sala, Sebastiano Campagna, Nina Chidian, a professor in Quebec, and all these others, I thank them for their collaborations. And these are of course, our in-house services. Without that, we can't do much. So this is the group from a few years ago, and I wanted to thank you. Merci beaucoup. I want to thank you for your time.
We take some questions, and then you can talk about
sure,
the exchange program, because I'm pretty sure que les va a interesar las oportunidades que tiene para los programas de intercambio de estudiantes, ya sea de estudiantes de doctorado o de grado, que algunos son con la Universidad de Montreal y otros son con Canadá, todo Canadá. So we have time for a couple of questions. Federico?
If I follow you correctly, in the first part of the talk you mentioned that in ruthenium complexes the energy difference between the pi star from the ligand and the Ig antibonding from the ruthenium center determines the lifetime of the excited state. Is that the case? I follow you correctly?
It's better when you see it in a potential energy well, to see that you can go over to the triplet MC from the triplet MLCT state. But there's a certain activation energy. And for ruthenium complexes at room temperature, there is sufficient energy to go over that activation barrier to get into the triplet MC, and that deactivates. It's not correct really to show it with a molecular orbital diagram, but the idea is similar. It's just for simplicity, that's why I showed it that way.
Okay. And I take that the ruthenium complexes that have the pyridine ligands pointing towards the nanoparticle bind to a nanoparticle by binding to a ruthenium 2 center, probably.
Presumably, yeah.
Presumably. And as the complex absorbs photons and transfers electrons to a nanoparticle, the nanoparticle reduces. And now that should turn ruthenium 2 into ruthenium 0, and that should weaken the bond.
I would suspect
then that complex will detach from the nanoparticle. That you mentioned that you were losing complexes from the surface of the nanoparticle.
But it's a second. So this they had showed it with other compounds. So there is a secondary sphere of interaction with the ones that are connected to the nanoparticle, and those are lost quite rapidly. But you still need photochemical energy. My own theory on this is, so we discussed this, luckily he was in Montreal just in July, that's when he gave me the slides. And so my feeling is that there's some that are monodentate and some that are bidentate. And it's the monodentate ones that are lost easily. And with two, sure, one pyridine gets kicked off, but the other one's still attached, so it diffuses back, it just attaches. So I think, he wasn't sure, and we'll do more experiments, but that might be a more rational explanation of how these are lost. And by that N1S XPS data, it's for sure there are many that are bound with two, because that was so small compared to the original. So there has to be many bound with two, some bound with one, and I think that's what the initial loss is. Those are quickly kicked out, and the other ones are more stable.
Great. Another question?
Yeah, actually about that experiment, which solvent were these?
This is, so for the nanoparticles, this synthesis in the studies, I think it was 3:1 THF methanol.
Okay.
And the way they isolate, you do the reaction, the reduction reaction with hydrogen gas, and you evaporate half the salt and add hexane, and then you precipitate out these nanoparticles. And that's I was surprised. I mean, it's not my field, but I mean, the dispersion was, 1.3, 1.2 plus or minus 0.2. I mean, for all the different, I was surprised, but that maybe others' field, not mine.
Okay, I was just wondering about the stability of the bond with the nanoparticles.
Yeah, these are fully washed, exhaustively washed.
Right.
So that's why it takes a
for experiments.
Yeah. So it takes the photochemical reaction to get that first loss, because those were the same solvent and fully washed ad nauseum, and they were solid. They're on. It's really the photochemical. And now that we discuss it, now I'm starting to think maybe it really is a 1 or 2 nitrogen binding that really makes a difference on the stability.
Great. Another question?
Just a very one. This compound that does not goes with the kasha.
Yeah.
It's quite interesting because there are few components that did you see some kind of spectral and in terms of dynamic measurements to see if this luminescence was real from the S2 or from the higher
Yeah, so this.
excited states, and because it's quite interesting to see a
So,
component.
if we do the calculation, if our thing is correct, it's something like HOMO -5 to LUMO +5. So it's really not, I mean, it's not HOMO LUMO because that's LMCT for sure. So it's really from a low energy, lower, more stable orbital, and that's the NCNO or component of the NC. Oh no, sorry, that's wrong. It's HOMO -1 to LUMO +5. So the starting point is the same as the LMCT, but it's the phenyl on the outside, not the inside. And because what we believe is because they're right beside each other, so they're perpendicular. Then you put 9 of them around, so there's not as much communication between this and that one. And the one in the center is part of the LUMO, so that's why it can deactivate more readily through the LMCT. So this excites, you can see it's 200 femtoseconds. So this is all done by femto, very short. This is then the vibrational relaxation is 1.8 picosecond. And even this, compared to these, is long-lived, but it's still only 20 picoseconds. So that's why this one we believe that there's this disconnection between the phenyl groups and why they don't. Or rather, the deactivation of this ILCT is because it's part of the LUMO, and that's what leads to this deactivation.
Great. So we can go to the other part of the talk.
Oh, I have to tell a joke though. Oh wait, it's in Spanish though. So I have to say, if you know the answer, don't say it because it gives people a time to think. It's a chemistry joke, and we've determined that in Argentina it would be first year university, or if you did some studying in a lot of studying in high school, maybe you learned it in your last year of high school. So remember, if you know the answer, don't say it. ¿Cómo se dice un diente en un litro d'agua? So a tooth in 1 liter of water. Don't say the answer if you know it. If you don't know, think about it. It's a chemistry question. Don't answer. Don't answer. Thinking about it? It's chemistry. First year chemistry. What do you learn in first year chemistry? The key is also un diente, un litro d'acqua. That's critical. It's not 10 liters. It's not 100 liters. It's un litro. So the answer is una soluzione un molar. So this is another one. Well, that joke works in French, English, Italian, and Spanish. It doesn't work in German because the tooth is called something different than molar. But they tell me that dentists in Germany, they use the Latin, so they call it molar, a dentist. So that joke only works at a